Solving exponential equations? Yeah, we're doing it. What is going on, math fans? Mr. B here again, bringing another sweet, wicked, awesome math video. This one a special request from one of my favorite students. Shout out to Ava. And we're solving some exponential equations with a common base. So that's the fiat with this, is that we won't be using logs. We're not there yet. So if you're looking for a video of solving exponential equations with logs, drop it down in the description. You'll find it. Maybe I'll post one of those little chummies around somewhere. If you're new to the channel, you know what to do. Subscribe, like, comment, all that stuff. All right. Let's get right into the screen. Let's get this going. All right. So solving exponential equations is one of those topics where you got to be really familiar with your exponent laws. So again, if you're just new to this topic and maybe you haven't done exponent laws before, this video is probably not for you. You might want to drop into the description, plug. There's videos, all that kind of stuff. Or just do a quick search and you'll find a bunch of great videos, I'm sure, on solving exponential equations. So with solving any type of exponential equations, we need to have, if we don't know logs, we need to have a common base. So what I mean by a common base is that we can write the base of this power with the same number, both of these powers. So we look at these numbers and we ask, well, 16 and 4. So you might ask, how can I get these to be the same base? So I always think of like what would be, when I have even numbers like 16, 4, 32, 64, they all have 2 in common. So 2 to the, 4 is 2 squared, 16 is 2 to the 4. Sometimes you get lucky, like in this one, where I can write 16 as 4 to the 2. All right, so I can completely replace this 16 with this 4 to the 2, and it's still the exact same equation. So I replace it like this. So that 16 is now 4 to the 2. It's not mysteriously gone. It's just rewritten into another form. So we end up with this. So the next rule is one of our exponent laws, which it basically states that if you have a power with another power on it, so my power is 4 squared, and my other power is x plus 1, that I multiply those things. So essentially what I have is 2 times x plus 1. Now the thing you need to remember is that 2 is going to distribute through. So it's actually going to look like this. Well, we don't need to do it in that step. Let's do it like this. 2 times x plus 1. We could distribute it if we wanted to, but we can also wait. And then I'll rewrite this side. So now what you notice is I have the same exact base on both sides. So when you have the same exact base, we're using one of our exponent laws. And I don't know if this has a particular name, but it's just one that I sort of reference all the time when I'm doing this in class with my students, which is that if I have some base, and some base being a, and it has an exponent n, and I have another base which is also a, so they're common bases. They have the same letter or the same number. And it has a different exponent, m. Then what I know that is that no matter what is in for n and m, what variables, what x's, they must be equal. There's no way around it. These exponents, even though I said they're different, they're not. They might have a value of x that works for them, like in this situation, that makes them be the same. So we can actually, once we get to this step with our common base, what we can actually do is let the exponents equal each other. So we go ahead and do that. All right. So now we've sort of taken away all the, the complicated math, and we're back in, maybe junior high or grade 10. When we're solving a linear equation. So the first thing we want to do is any brackets, we want to get rid of them. So we're going to expand just by multiplying through. And we do that. So 2x plus 2. That equals negative x plus 1. So the next thing we want to do is we want to get the x's together. So it doesn't matter what side, where they go, but I'm going to choose to add x here to both sides like this. That looks like a multiplication symbol. Let me get out my eraser. Everyone just cringes when I get this thing out. All right. And while I'm at it, I'm going to choose a different color pen. I'm working on getting a new, sort of a new setup, guys. So like, and in the meantime, I'm kind of stuck with this old one, but we'll see what happens, okay? So I end up with this setup here. So I got 2x plus x, which is 3x. So 2x plus 1x, now I have 3 x's. And then plus 2 equals 2. And then what I want to do is I want to solve, get the numbers together. So I go ahead and subtract 2 from both sides. So I go subtract 2, and then I end up with 3x, and these cancel, and I end up with 3x equals 0, and then I want to divide by the number that's in front of the x, so I get x is 0. So 3 divided by 0 is 0. So that's our solution. Now, one of the best things about this is that you can always know if you're correct. So if you end up with a solution like this, all we got to do is go back to the top and actually just check by plugging in that number. So if I go 16, 0 plus 1 equals 4, negative 0, even though there's no negative 0, but I'm just staying true to the equation. And these two sides should equal each other if we did it right. So we got 16 to the 1. Well, that's 16. And then we got 4, and then 0 plus 2 is 2. 4 squared is 16. So we got both sides equal to each other. We have a correct answer. All right, so the answer to this question is x equals 0. So let's sort of progress a little bit with a slightly more complicated question. And I'm planning on this video to be a little bit long, guys, so I'm not too concerned if I go a bit long. And we have a situation here. It's very similar to the last question. We have two bases, 1 over 9 and 27. And we need to try to make them common. So you got to sort of think a little bit mathematically when it comes to this. Like, what does 9 and 27 have in common? Well, 9, for example, is 9 is equal to 3 times 3, which is 3 squared. Okay? And 27 is 3 times 3 times 3, which is 3 cubed. So again, that kind of stuff, it takes a little bit of practice to sort of train your brain, but once you start thinking common bases, then it really starts to sort of click in. So what I can do is I'm going to change this 1 over 9 to 1 over 3 squared. And then my exponent still stays 2x plus 1. And then this 27, well, that's the same as 3 cubed. So I'm changing the exponent to 3 cubed. Note that I haven't changed the equation. Okay, so this thing, 1 over 3 squared, is still 1 over 9. 27, still 3 cubed. All right. Now, we don't have a common base yet. We're close, but if we want our common base to be 3, what we need to do is flip this exponent over. So one of the other exponent laws that I know, and my neighbor just started, is a very loud car. So if you can hear that in the background, I do apologize. So one of the things that you notice or one of the exponent rules that I teach my students is that if we have a negative exponent on the bottom, or a exponent on the bottom, not negative exponent, let's just say x to the n, then we can take that to the top and make it x to the negative n. And the opposite, of course, works in reverse anytime you want to do that. So I have a 3 squared on the bottom, just like my x to the n. If I want to get rid of the 1 over part, all I need to do is make my exponent negative, just like that. And I've eliminated that 1 over part. But this, again, these are still exactly the same. 1 over 3 squared is exactly the same as 3 to the negative 2. I end up with 2x plus 1. And then I have this again. And I'm going to rewrite this one more time just to, again, try to drill home the fact that we're going to get the bases to be exactly the same. So remember my rule about if I have a power over power, we multiply the exponent. So here I have a power over power, negative 2 times 2x plus 1. So negative 2 times 2x plus 1. And then over here I have 3 cubed, which is 3x minus 1, just like that. So what we want to do now is we want to try and use our rule where if we have common bases, then the exponents must be equal. So we take the exponents. no matter how complicated they are, and we let them equal each other. So we go -2, 2x plus 1, and then 3x minus 1. And then all we do is we distribute both sides. So we're solving for x now. So we're back in linear equation territory, just like this. So I end up with negative 4x minus 2 equals 3x minus 3. So we distribute, making sure to multiply both things in the brackets. And then I'll subtract 3x from both sides, and I'll subtract 3x from both sides. And that gives me negative 7x minus 2 equals negative 3. And then I'll add 2 to both sides. So add 2, add 2. So these cancel, just like these should. And then negative 7x equals negative 3 plus 2 is negative 1. Then I'll divide both sides by negative 7. And again, we don't always get good numbers with these. 1 over 7, not that fun of a number, but it doesn't matter. Okay. Now, I'm not going to check that. I don't have a calculator with me right here at the moment. But you could easily go back and check that answer by plugging in the numbers. And if I was on a test, that's absolutely what I would do. And if you have a multiple choice question, you could even just do that with the choices that you're given and sub them in. All right, let's go ahead and try a slightly more complicated type of question. So we've got another situation where we have an exponent. We're trying to solve for the exponent, and we've got an 8 here in front. Now we got a couple of options with this 8. My preferred option is to check and see if 128 is divisible by 8. So if I go and divide 8 on both sides, hopefully I can get something that I can do a common base of 2. But that's not the only option, but that's the first option. And actually, I'm going to have to get a calculator for this because I can't do 128 divided by 8. So, here's one. 128 divided by 8 equals 16. Lovely number. 2x plus 3 equals 16. And then, of course, we can write 16 as base 2. And that can be written as 2 to the 4. Now, one of the mistakes I often see my students trying to do is changing the numbers and then not thinking about whether or not they equal. So, for example, someone might say, okay, let's just put an exponent 4 right here, and then I'll have 2 to the 4, 16 is equal to 16, we're good to go. That's not how we do common bases. We have to take the number we're given and we have to change it so it has the exact same value. So the thing is, 16 is exactly the same as 2 to the 4. If I put a 4 here, I have 16 in here and 16 here, but that does not give me a common base. All right? That is a mistake. I've changed the equality of this 2. There's no longer the same equation. So you have to make sure that everything remains equal on the way down. We're just changing the number to a different form. So now that I have this, I have x plus 3 equals 4, and this one's going to work out really nice. Minus 3, I get x equals 1. And there it is. Now the other option, which I think is not as easy as that one, is to change this 2 to a base 2 as well. So the problem with, change this 8 to base 2 as well. The problem with that is it's not always going to work. You're not necessarily going to get a number out here that's going to be able to be written as a common base. So my instinct is if you can divide it, get rid of it right away. All right? In which case, 99% of the time, you will be able to divide it. The only time you will not be able to divide it is if there's a number or a variable here and that just doesn't work, it doesn't divide, or it's in brackets or something like that. So in that scenario, you won't have a choice. Maybe I'll make a video on one of those scenarios. And I don't know, we might have something coming up. So this is another scenario. You got a variable, you got a number on the outside here of 3, and we want to simplify this for ourselves. So we go ahead, divide by 3. So I'll do 96 divided by 3, the old Casio. Still looking for a sponsorship from Casio. They retweeted my tweet though. That's pretty significant happening. And we end up with this, and that's 32. So now we have to, again, think common base. So what do 4 and 32 have in common? So you think about like 4 is 2 times 2, 32 is 2 times 2 times 2 times 2 times 2. I think I said it 5 times. So 2 to the 5. So it becomes 2 to the 2. And again, I didn't change the equality. That still equals 4. And then 32 is 2 to the 5. And again, that still equals 32. Nothing has changed. I didn't manipulate these in any way. I just changed the form. They still equal the same thing. And then I'll let my exponents equal to each other. So I know I'm going to have to times these. So I can sort of skip that step if you want to and go like this. 2, 3x minus 1. As long as you understand these are multiplied together and this equals 5. So now I can distribute through with the 2. So I get 6x minus 2 equals 5. This is my belly growling if you heard that. Then I'll add 2 to both sides just like this. So I get 6x equals 7. Divide by 6, divide by 6. And then I'll write it up here. X equals 7 over 6. So again, not a good number, but you know, doesn't matter. As long as we did the technique right, we got to be confident. All right, so this one I think is our last one, and this one, let me tell you, is a spicy meatball.
Mamma mia, that's a spicy meatball.
Yes, very spicy. All right, so we've got a lot going on with this one. We've got 125, 25, 5, 1 over 625. So again, you got to think about what could possibly be my common base. So all these things have 5 in common. 125 is 5 to the 3. I think so, yeah. 25, 5 squared, 5 is already good. 625, I think that's 5 to the 4. Let me just double check. 5 times 5 times 5 times 5. And it is 5 to the 4. So we got to start by rearranging all this stuff and see what we can make happen. So, and again, don't be intimidated. It's a spicy meatball, but we'll get it done. So 125 is 5 to the 3. Still equals 25. It still equals 125. I have not changed the value of my equation. And then times 25 is 5 squared. So again, have not changed the value of that base. It's still 25. I'm just putting it in a form that's a little bit more friendly to us. All divided by, my hand is going to like fall off at the end of this question. And then 5, 3x minus 1. So the next thing I'm going to do is I'm looking at this 1 over 625. So I'm going to worry about changing the 625 first. I'm not going to do everything in one step. So 625 is 5 to the 4, all to the negative x over 2. So one thing we need to remember is that a negative exponent means we can flip the base. We flip bases, not exponents. That's what I always tell my students. Flip bases, not exponents. So this is going to change to a positive, and I'm going to flip that over eventually. So I don't know what's happening upstairs in my house. If you heard that noise, it sounded like a plane. So we'll do some multiplication here. So this one here, I'm going to just take the 3 on the outside, get my common base of 3, and then I have x plus 3. So they multiplied, times, and then I have the 5 here, and that's 2 times 2. So this one I can actually multiply and make it 4, x plus 1. And that's all over 5, 3x minus 1. So don't be intimidated by this. We'll break it down step by step, okay? And this one, I'm going to get rid of this negative exponent here, and I'm going to flip my base. So this becomes 5 to the 4. And then my exponent that was negative x over 2, now it's x over 2. Common mistake, flipping that exponent. Seen it a billion times. We, here at Math with Mr. Barnes, we flip bases and not exponents. Keep that in mind, okay? So, I know this is a long video, but hopefully you've stuck around for the whole time. And we're almost there, all right? So let's go ahead now and multiply through with the 3 and the 4. And normally I wouldn't do this, but since this thing is so complicated that I just want to really slow it down for us, okay? So this one becomes 3 times x is 3x. 3 times 3 is 9. So 3x plus 9 times. And then this one multiplies through 4 times x, 4 times 1. So that is 4x plus 4. And then all on the bottom here, I've got the 5x, 3x minus 1. So that one's all gold. And then this one here, I'm going to multiply 4x divided by the 2. So that's 4x. I'll do it right here, 4x over 2. And just to save myself a step, we can call that 5 to the 2x. All right. So when you have multiplication and divide, we got to rely on a little bit more complicated of our, well, I want to say complicated, but one of the more often forgotten rules when we're doing solving common basis. So when you are multiplying, so 5 to the, I'll just call it 5 to the 2 times 5 to the 3, the rule is multiplying powers to the same base, we add the exponent. That becomes 5 to the 5. So what we have to do here on the top of this thing is where we're multiplying, we have to add the exponent. So we're going to go 3x plus 4x. So that's going to be 5 to the 7x. And then 9 plus 4 is 13. So 7x plus 13, all divided by 5. 3x minus 1 equals 5 to the 2x. So now I have a division left, or dividing. So when we're dividing, so I have 5. Let's go 5 to the 5 this time, divided by 5 to the 2. When we're dividing, we subtract exponents. So that ends up being 5 to the 3. So I'm at 5 subtract 2, it's 3. So here I have the subtract exponents. With this, we got to be very careful with the signs. So I go 7x subtract 3x, so that's 5 to the 4x. And then 13 subtract negative 1, that is a positive 14. So 13 subtract negative 1 is the same as adding 1, so 13 plus 1 is 14. And that, of course, equals 5 to the 2x. And then the next thing we can do is what we've been doing in the first examples, which is let our exponents now equal each other. We've got the common base. We let them equal each other, and that equals 2x. So 14 plus 4, 4x plus 14 equals 2x. So I don't like the location of this 14, so I'm just going to move it to the other side. So subtract 14 like that. These go away, so I get 4x equal 2x minus 14. And then all I'm going to do then is subtract 2x. And I know some people are screaming at their TV screens or phones and saying, why didn't you get rid of the 4x? It's just like, I'm so crusty and old that I'm not changing my ways. And variables always going to left for me. That's just the way they are. But if you're new and you're hip and you're one of those risk takers, you go ahead and put the x on any side you want. You live YOLO. You only live once. And then, of course, we divide by 2, and I get x equals negative 7. And there it is. That will be, if I was on a test and I got that one and I got negative 7, I will be jumping out of my shoes that, wow, it's a good number. So definitely want to check that one if you have a chance. If you stuck around for the whole video, guys, good for you, because now you get a chance to hear me say, peace. See ya!
A lot of boring math later.